Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey, Houston, we don't have a problem. Today we want to talk some more about inclined planes, but today we want to talk about how to do, if you will, calculations with these. I think my pins are about toast here. All right, that one's done. All right, I think you can sort of see calculations, but let's do a problem. All right, so we've got an inclined plane. So let's do sort of a problem. Let's say that I have, I'll write it out here. How far up a 200-meter ramp will a train go? How far up a 200-meter ramp will a train go that has an initial velocity of 12 meters per second if the height of the ramp is 60 meters? So I've got a ramp, I'm going to draw a picture. I have, this is 200 meters, right? And this is 60 meters. So I want to find theta first, because I want to find what the acceleration of gravity is. So this is the opposite and the hypotenuse. So I can say the sine of theta is 60 over 200. So I'm going to take the inverse sine. I don't know what the angle is. So I'm going to take the inverse sine, or sine -1, of 60 divided by 200. And that is a 17.5. So theta equals 17.5 degrees. Got it? So we've got a car down here, if you will. By the way, we're assuming there's no friction. And he's got an initial speed of 12 meters per second. He's going to go up. So it's like he's pushed. He doesn't have like an engine or anything pushing him up. 12 meters per second. He's going to go up, and he's going to slow down, and then he's going to reach some height. How far up the ramp will he travel? Now remember, what's going on also, vectorially, is we also have an acceleration. But remember, we learned in the last video that in this problem, acceleration is super easy to do. Acceleration on a ramp is g sine theta. So let's find what this is. The acceleration is g, which again we'll assume we're on the Earth, so 9.8 times the sine of, what was it, 17.5. So let me figure this out. So 9.8 gives me 2.95 meters per second squared. So now what we have is we have a kinematics problem that we can just play the x and the y game, right? So we know x0, we'll just, so this is x, is 0. X, or let's call it x1. x1. x2, we don't know. In fact, that's the question we're asking. How far up the ramp can you go, right? What else do we know? We know V1 equals 12. Now we know V2, even though it's not told, because how far it's going to roll up the ramp and stop before it turns around. So V2 is 0. We know acceleration is actually negative 2.95. So this should be a negative sign. Meters per second squared. And then we just have t. We don't know that either. Well, we could ask that question, but this question is asking for V2. We can then look at our three key equations. And if you look at the three key equations, one's going to hopefully stand out to you. You can say V2 squared equals V1 squared plus 2 times A times delta x, or just the change in height. So V2 is 0 equals V1, which was 12, now it's squared, plus 2 times negative 2.95 times delta x. I can just say d, or the distance it's going to travel, right? So if I subtract 12 squared, or 12 squared, I know that, that's 144, so that'd be negative 144 equals 2 times negative 2.95 times d. So I'm just going to solve this problem. I get D, or you can call it dub X equals D, whatever, and I get 24.4 meters. So that means it's going to travel up, it's a 200-meter ramp, it's going to travel up 24 meters, and it will stop. If I wanted to find time, you would just plug it back into the equations. This is just like we've been doing kinematics problems. And now that you know V1, V2, et cetera, you could easily find the time of the total, or the time to the top if you have V1 and V2. By the way, when it comes up, it's going to have to the 20 meters or 24 meters, it's going to have a velocity of 2, but it's going to come back, it's going to have a velocity again back of 12, but 12 in the opposite direction. If you wanted to get that. And then what happens after the ramp would be an interesting question, because now we don't have then there's no acceleration because it'd be on a flat plane. Because you know what it would really do is it'd travel up 24 meters, come back, and moving at 12 meters per second, and assume there's no friction loss, which there would be. It would then go off at a constant speed here, assuming no friction for forever. But of course, we know in the real world, friction would take over and eventually stop it. But the key on this is this right here. Is you're not going to use 9.8, you're going to use a fraction of 9.8, and the fraction is g sine theta. That's how you do inclined plane problems and calculations. Houston, we don't have a problem.